Hello. We are starting the ML-2 doubt clearing session. Uh, in this session, if you have in this first 1 hour or so,
Hello.
like
We are starting the ML-2 doubt clearing session. Uh, in this session, if you have in this first 1 hour or so,
Hello.
We are starting the ML-2 doubt clearing session.
yeah, hi everyone. Yes, so we are starting the session on ML2 audio ML2 doubt clearing session. Yeah, sorry for the echo. There are some like two windows are open, so there are some echo. Yeah, if you have any question, so in this, yeah, it will continue till 10:30, and if you have any question particularly on the topics which I covered, like on Bayesian networks, feature selection, PCA or LDA. You can ask questions on those, and I would be happy to cover if you have any concerns. Also, there is no video feed here. I mean, we'll just have the audio feed. I am unable to switch on the. Don't have the camera and all these things set up properly, so we'll just have the audio thing. You can just type your questions, and I'll be responding through audio. So, okay. So the first question we have here is on Bayesian networks that weight grass is okay. Weight grass has conditional independence with cloud since it is not directly connected to it. We can use these conditionals with sprinkler and rain. Just let me open the example once on my end. So yeah. So if you look at the Bayesian network, I mean the wet grass, there are directed edges from sprinkler and rain, and then sprinkler and rain have directed edges from cloudy. So wet grass. So when sprinkler and rain, those variables are observed. Wet grass is independent of cloudy, but when any of these is unobserved, there are paths. Wet grass will have some dependency on cloudy. So if you follow the baseball algorithm, you will see that how this conditional independence works out. So when sprinkler and rain are given, that we know we have some information of if the sprinkler is on or off, or we have some information about the rain being on and off, then we can just assume that the wet grass is not dependent on cloudy because the path is closed. But if any of these is not given, then there is a path and wet grass will be dependent on cloudy. Okay. Huh. So okay, please. So one thing which will be helpful here, if the full question, just put in one comment. Don't split it into multiple comments, so that we can attend one question at a time, one comment slash question at a time. Just to be clear, yeah. Okay. Okay. So still okay. So so. See, I mean, if there is the wet grass, so there are two. So if you look at the cloudy and wet grass, there are two paths: one through the sprinkler variable and another through the rain variable. So even if any of these paths, so both of these paths needs to be blocked. If you sort of completely cut out the relationship between wet grass and cloudy, right? So there are two paths you can see, right? Cloudy sprinkler wet grass, cloudy rain wet grass. So there are two paths. If you want wet grass to be completely independent of cloudy, both of these paths needs to be cut out. So sprinkler and rain, both of these should be given. Okay, only when both of these are given, wet grass will be independent of cloudy. Okay, that's how it works. But if any one of this is given, one of them is given, not given, then there is still some independence. Okay, so okay, I understand. Okay. So does that make sense? The path thing or this Bayesian network, does it make sense? Or then we can move on to the next question if this part is clear. There is no notion of what do you mean by second order? No, there is no notion of second order dependence here. I mean, it's just, I mean, there are all this. The only the edges define the dependencies here. I mean, every two variables are dependent only if there is a detected edge from one of the node to the another node. Okay, but when one of the variables are not observed, you will have to marginalize to all possibilities, right? So then there are dependencies to other things come out. Okay, there is it's just the all the dependencies are defined by the ages given. So okay, so another question is about this eigenvalue decomposition and LDA. We have another question about, just to be clear, LDA performs scatter matrix, and then eigenvalue. Okay, then eigenvalue. So, so LDA, it's a little bit different. Are you talking about the PCA where we compute the covariance matrix and do the eigenvalue decomposition there to get the eigenvectors and eigenvalues? Because the LDA, the solution becomes a little bit differently. We basically do this. If you look at the slides, we did an optimization of the cost function, which was a ratio of the between class variance and within class variance, and then based on that, we had an eigenvalue problem, and we had a trivial solution to that eigenvalue problem through this SW inverse mu1 minus mu2. Okay, so yeah. Yeah, so PCA you do covariance and then eigenvalue decomposition. LDA you don't need to do that. LDA you have a very simple solution, which is the inverse of this within class matrix SW and mu1 minus mu2. That gives you the solution for two classes. For C classes, it becomes a little bit complicated, but yeah, I mean, but it's sort of similar. I mean, this is the first direction which you. This is the direction where you want to project for two class basically. Yeah, correlation. Okay. Any other question? Yeah, baseball. Yeah. Okay. So let me open the slide. Baseball. Yeah. So, so the see the so the baseball algorithm. That's basically this basically is a complicated structure, right? Sometimes the relationships are very complicated. There are a lot of dependencies are there. So baseball basically tries to give you some simple rules to sort of determine when two nodes are dependent and when two nodes are not independent. Okay, and they are basically defined. So please, if you have the basenet slides, please open the baseball algorithm slide. That will help you here. Okay, please open that slide. So you can see that there are basically there are different nodes. Okay, and basically we want to see how much information flows across nodes. Okay, so we already talked about this example, right? Wet grass, sprinkler, cloudy. So when I said that the sprinkler is so when cloudy and wet grass, they are independent. Okay, that means there is no information is flowing. Okay, but when they are dependent, that means there is information flowing. Okay, so independence means there is no information flowing. Dependence means there is no information flowing. Okay, now how did it achieve independence? Independence it achieved when the sprinkler is on and the rain. This information, these variables were observed. Okay, so that case we what we said that then these are basically stopping the information flowing from cloudy to the wet grass. Okay, those variables are specifically stopping the information flow. That's why wet grass and cloudy, those variables are becoming independent. Okay, because the information flow is being stopped. But when these variables are not observed, then the information can flow freely. There is independence can come out. Okay, so all these things, whichever I am telling, baseball lets us gives us a little bit more structure and systems and rules to determine these dependencies. Okay, so yeah. So yeah, it's a little bit it's a little bit non-intuitive. I agree on that, but yeah, if you think clearly, it does make sense actually. So so see, the explaining away things is a little bit more complicated. I mean, let's get to that a little later. First, let me cover the baseball algorithm. So there are two scenarios. There are three different scenarios here. Okay, one scenario we have one node, and then there are two edges coming to that node. Okay, now we want to determine if the information flows through that node or not. Okay, so that's what we want to determine. Now if now what baseball says you that this if this variable is not observed, then the information doesn't flow. Okay, so this is, we are talking about two incoming edges. Okay, if you have opened the slide, that is the first column we are talking about. First column only. Okay, first column, not the next three columns. First column, where the first row we are first column, first row we are particularly talking about. If it's white, the node which we have which white, that means this variable is not observed. That means the information cannot flow. Okay, whereas if this node is observed, then the information can flow through this node. Okay, so that's so this is the first scenario of baseball algorithm, and obviously this will also explain the this will also give you the explaining away factor. Okay, we'll come to that once the baseball algorithm is explained completely. Now if you look at the next column, uh, there are again, I mean, when the in this case the node has two outgoing edges. Okay, earlier we had the node and we had incoming edges. Here we had outgoing edges. Here the thing just reverses. Okay, when the information is not observed, the information can flow. Okay, flow through this node. Okay, because there are outgoing edges, the information can flow. But when the node is observed, the information cannot flow. Okay, so this is very similar to what we have already told, that when in Bayesian network, if any of its parent is observed, the information doesn't flow through that. Okay, so it will stop. It will not be dependent on its parent anymore. Okay, or on its like grandparent anymore. Okay, so whenever your parent is seen, then you are not dependent on your grandparent. But when your parent is not seen, then you have some dependency on your grandparent. So that's what this part says. Okay, and the third is also very simple, that's one node and you have one incoming and one outgoing edge, and you have to see if this information flows. So if there is a parent node, okay, and parent node has one incoming node and one outgoing edge, then if this parent node is not observed, then the information obviously will flow. But if the parent node is not observed, then the information doesn't flow. I know it gets a little bit complicated here. Yeah, I mean there are three different scenarios, and then there are sort of the treatments are slightly different. But if you see the first, so the first scenario is very complicated. The first column, okay, where both are incoming edges. But when there are both are outgoing edges, or one incoming and one outgoing, you see that the principles are same. Okay, so the last three you can think of one group, and the first is another group where the treatment is just reverse. Okay, that's how you can easily remember it. And yeah, so that's does it make sense? We'll come to the explaining away, but the baseball. Okay, assuming it makes sense, we'll just look at the explaining away factor. So in explaining away, what happens? So again, I mean, please open your slides. Just refer to the slides where we discuss the explaining away concept. Okay. So there are two variables, right? Sprinkler and rain. Okay, and they were so if you ignore the third variable, grass is wet, they were marginally independent. Okay, there are no dependencies. Okay, and let me connect to the baseball algorithm here. Okay, so if you do not have any information on the third variable, that if a sprinkler is on or sprinkler is off, we do not have any information, then they are independent. Okay, there is no dependency on those two variables, sprinkler and rain. But if you know, okay, if you have information about the third variable, that the sprinkler is on, okay, and sorry, if we have the information about the third variable, that the grass is wet, and we know it's raining, then you can see that the probability of sprinkler is 1, given grass is wet and raining is 1, is 0.1945. So the probability decreases. Okay, but if you earlier case, when we computed the probability of just sprinkler equal to 1 when the sprinkler equal to 1 when the grass is wet. Just 1 second. Raining, and we know that it is raining. Yeah. So yeah. So yeah. So yeah. So when if you look at these two examples, right? I mean, when we are computing the probabilities, so probability of 1 second. Yeah. Okay. So yeah, just let me explain that. So when it's a little becoming a little bit inconvenient, because yeah, I mean, I am unable to refer to the graphical model which we have here, the cloudy, sprinkler, rain, and wet grass. If you see that the sprinkler is on, okay, please open the explaining away slide and let me go over it once more. So one scenario, we had the sprinkler is sprinkler equal to 1 when the grass is wet. Okay, what is that probability? if you see that probability was like 0.43. Okay, the probability was 0.43. When you know that the grass is wet, the sprinkler is 1. Okay, but if you see that we also, if we have the information about it's raining also, then the probability of sprinkler equal to 1 is decreases actually. Okay, so that happens because we have, because whenever there is the rain and the sprinkler, these two information gets connected through the grass is wet variable. Okay, if you remove the grass is wet variable, this sprinkler equal to sprinkler and rain, these two events are completely independent. But when this grass is wet variable is observed, then the variable dependency comes into the picture, and that comes from this comes from the first column of the baseball algorithm. Okay, if you see that when it's not observed, they are independent, but whenever it's observed, there is this dependency comes into the picture. This explaining a factor comes into the picture. I agree. Yeah, it's a little bit more complicated. I mean, a little bit complicated. I mean, it's just it's more a little bit. I mean, one thing is you can try to do this mathematically. You can see like when the variables are observed and non-observed, how this marginalization and independence works out in this thing. So you can just take simple examples and see if this variable is not observed, what is my probability? If this variable is observed, what is my probability? And that way you can try to figure that out. If we are intuitively, it's hard to imagine, but otherwise it's a little simple. It's just all about these paths and the connections and if the variables is observed or not observed. Whenever this there is observation, that there is a chance that the information flow will either stop or either start. So you'll have to see what is the kind of connection there is, and based on that you'll have to decide. Okay. But I believe, yeah, if this basic construct of the Bayesian network is clear, these things should be clearer. I mean, as you sort of try to work this out, should be clearer. Please try to get those probabilities done and compute those probabilities with your hand. Try some a little bit more complicated Bayesian network, perhaps. Then things will perhaps become even more clear. More clear. Okay, there is one question about choice of either using PCA or LDA, depends on kind of problem we are solving. If so, LDA mostly useful for clustering only. So now PCA and LDA, it's a very sort of clear differentiation when people use PCA and LDA. So if you see PCA or principal component analysis, which we came out, which we discussed, that was for data where we didn't have supervision or labels associated with the data. Okay, we just have a bunch of samples with just features. We do not have any labels with that. We do not know if this belongs to images of cats, this belongs to images of dogs, or some kind of label or supervision were not there. Okay, so that's where you use PCA, where you try to find the direction of the maximum variance in the data and project the data into the direction of maximum variance. Whereas in the case of LDA or linear discriminant analysis or Fisher discriminant analysis, the situation is, yeah, along with the data, we also have labels. We know that these are the samples which are belong to the cat, and these are the samples which belong to dogs. Okay, so now how do we find a projection where these samples are, the difference between these samples are captured out? Okay, so we try to project in a direction where the cat samples are as far as possible from the dog samples, where the cat samples among themselves are closely clustered and dog samples among themselves are closely clustered. Okay, that's how this LDA thing basically works out. So the major difference is whenever you have training data and you do not have labels, you use PCA. If you have labels, you try to use LDA because you want to exploit the labels associated with the data. So if so, is LDA mostly used for clustering only? No, it's not true. PCA is more useful for clustering. LDA is not. I mean, the LDA you cannot use if you do not have supervision. So there is no value of LDA there. Yes, yes. Okay. So yeah, SVM. I think, yeah, I think SVM will be covered after 10:30. In this session, we are trying to cover Bayesian networks, PCA, LDA, and feature selection. Yeah, I mean, yeah, and SVM will be covered. I think we will be covered by Mainul. Yeah, any more question? If PCA, LDA, feature selection or Bayesian network, any more question? Anything? Uh, okay, so is there any specific reason why we should use feature selection than PCA-LDA? Yeah, yeah. Yes, yes. Yeah, first let me answer this question. Is there any specific reason why we should use feature selection than PCLDA? So the main difference between feature selection and PCLDA is this. In feature selection, we have a bunch of features. Out of that, we we select a subset of features. Okay, whereas in PCA and LDA, we find the direction and we project the features to that direction. So in feature selection, whenever so suppose you have like four features like say height, width, length, and breadth. Suppose these are four features of some classification. Now, when we are choosing, when we are doing feature selection, we might find out, okay, maybe height and weight are the most important features. The rest of the features don't matter. So we select these two features. Now, the advantage, one of the major advantages, these two features are belong to the original set of features which we had. Okay, so these two features are human interpretable. So we can explain that, okay, these are the features and these features are human interpretable. So it is often useful in business scenarios where you are suppose part of a company, you are dealing with business teams. Whatever features you say are important or you are using in your model, you'll have to say that why it's important. Okay, so why so you'll have to give some human interpretation. Okay, so in bank, for example, if you are stopping someone's credit card or if you are terminating someone's credit card, you'll have to give the explanation that why this particular feature was used. So it's better to be human interpretable. On the other case, PCA and LDA, these are projected to a defined direction, and in the projected space, each feature doesn't make sense. Okay, so the feature which you might get is like 0.5 into height plus 0.3 into width plus 0.1 into breadth. Okay, so that feature doesn't have, it's a combination of different features. That feature doesn't have any like one particular thing in it. Okay, so it's less interpretable. So that's the problem with PCA and LDA. But having said that, a lot of like even deep learning has that problem. Deep learning also often the things are not interpretable because there are a lot of processing that happens. So it's very hard to explain why things are happening. But problem is the advantage with deep learning or even sometimes maybe PCNLD is that might give you better performance. Okay, if you have the, if you can take handle the, if you need the better performance, if you do not care so much about human interpretability, you go for this PCALDA. But if you care a lot about this human interpretation, all of this, I think you would go for feature selection. Okay. Uh, okay. The next question is the probability of say rain when cloudy is give probability of say rain when cloudy is given and not estimated, right? Cloudy, the probability of say rain when cloudy. Just let me open the slide again. Rain, rain. Yes, yes. Yeah. Probability of rain given cloudy is given. It is not estimated. So in this particular example, these are given through this conditional probability tables or conditional probability distributions where these probabilities are given. So it might not always be given these probabilities. These probabilities might, you might have just data. From that data, you might have to estimate these parameters, that what is the conditional probability distribution or conditional probability table. You might be given like how many times historically when it was cloudy, how many times it rained, when it was not cloudy, how many times it rained. So all this historical data you might be given, and you might need to actually estimate those parameters in practice. But in this particular example, it was given when it's cloudy, what is the probability of rain and so on and so forth. It was given. Yeah, we do not need to estimate that. Yes, yeah. So yeah, you can use a frequentist approach. Yeah, there is no issue with this. So yeah, so see this kinds of scenarios, some kind of discrete scenarios, you can just use this frequency basis. Some kind of scenarios you might have to assume some kind of you might have data which is you might assume some like distribution, like Gaussian distribution or something like that. Okay, if you look at this, one of the good example of this graphical models is LDA or there is another LDA which we didn't get a chance to discuss, like latent Dirichlet allocation, okay, which people use for clustering text documents. There people use graphical models, and there they use like different kinds of distributions, and they are estimated in a different way. They are, instead of this use this frequentist basis of probability estimation, they use like more of likelihood and prior kind of approach they take. Okay, but yeah, depending on data, you can use both, just simple frequency based yeah. L1 is, yeah, L1 is Manhattan, and L2 is Euclidean distance. Yeah, L1 and L2, like one of the differences L1 people use when you want more sparsity in the data, and L2 you don't really matter about, it doesn't matter about the sparsity. The weight vector, you can just get like a normal weight vector. There is no sparsity is not enforced. So if height, weight, breadth, and weight, if these are the features, what L1 will try to do, L1 will maybe select just two features and give high weight to those two features and give zero weight to other features. Whereas in L2, you might give like low weight to all four features. So that's how the prioritization is done. For feature selection, yeah, if you are thinking about in terms of feature selection, then L1, L1, I'll come to that. L1 basically encourages more of feature selection kind of approach. Okay, the sparse and dense, the difference is this, that the sparsity means like you have like four features. You will try to select. So when you are learning this weight vector, you are trying to give a high weight to maybe one or two of those features and give low weight to the remaining features. Whereas in dense, all of your values might be very close, like 0.1, 0.2. So let's take an example of a sparse vector of 4 dimension. Okay, it will be like 0.01, then 0.9, 0.8, and 0.02. Okay, so you can see there are two values which are extremely high and two values which are almost close to zero. So you can consider those values as zero. Okay, so this is a sparse example of a sparse vector. Actually, in practice, it happens that out of like 100, you will have like 5 or 10 maximum like non-zero, and rest of them are close to zero. Whereas dense, out of 100, and maybe almost 70, 80 are non-zero values, and none of them you can throw in zero. Okay, there is not much difference between values. Okay, so that's what is called basically dense. Okay, most of these values are non-zero, but they might be small or large, whatever, depending on how it is. Okay. Yeah, so sparsity is desirable in a lot of scenarios. So in regularization or in feature selection, sparsity is desirable. So if you have a bunch of features and you want to do, like say, feature dimensionality reduction, you might want to enforce sparsity. Okay, and sparsity basically it's in sparsity. The problem with sparsity is the advantage with sparsity. It enforces this regularization in a strict way. Okay, so obviously if you have a lot of features, you like thousands of features and like tens of thousands of features, you know that all of those features are not useful. Okay, only a subset of those features are useful. So obviously you might want to enforce some sparsity to determine which features are more useful. Whereas the problem with sparsity is optimization becomes a little bit more tricky, and some approximations etc. are done. Uh, but uh, but sparsity basically helps you to determine like select features in a much better manner than L2 regularization. Oh, blanks is also- No, so sparsity is not. Yeah, sparsity is blank cells. So sparsity is cells where most of them are blank and some of them are non-zero or non-blank. Okay. Yes, the sparsity. Yeah, with sparsity you get definitely better feature selection because some of the features are forced to have weight zero, where some of the features are forced to have higher weight. Okay. Okay, so yeah, that's a good question. So one of the limitations of LD is class has to be represented by unimodal Gaussian. If the class is not unimodal Gaussian, are there methods to convert it to unimodal Gaussian? Uh, yeah, so the thing is, the unimodal Gaussian. Just let me think a little bit. So the problem is, yeah, I mean, so this see, I mean, this is a very generic problem in machine learning. I mean, this unimodality, bimodality. I mean, even in clustering or any LD or all these scenarios, this is a problem. If the data has multiple modalities, it becomes very hard to model that data. Okay, even if you are, even when people assume that these distributions are Gaussian, people assume that they are unimodal Gaussian, and it's very hard to do any work with those kinds of things, right? I mean, uh, you are limited basically to the Gaussian assumption, okay, and unimodal assumptions. So I don't know, and I don't think that it's a good idea to convert data to unimodal Gaussian before processing, because you might, when you are trying to convert to unimodal Gaussian, you might lose some of the information. So obviously, it might be feasible to project in a direction where the bimodality is wasted. Okay, bimodality is basically taken away and the data becomes unimodal, or sort of close to Gaussian. You might be able to project in that direction. Okay, but I don't know if that's a good idea. So if your data has bimodal or trimodal distribution, I don't know if it's a good idea to project in a way which basically takes the bimodality or multimodality factor out of the account. Okay, so a lot of this non-parametric models, or this kind of, recently there are this lot of this adversarial learning techniques. Some of you might have heard about this generative adversarial learning techniques, where it's very data driven and doesn't assume a strict parametric formulation such as a Gaussian distribution, which can generate which can sort of generate or sample from this multimodal distributions. But yeah, there are also challenges with that. I mean, optimization and everything is difficult. But yeah, coming back to your question, you might be able to map into a unimodal Gaussian, but it's not a good idea, I think, because you will take the juice out of your data, which might hamper your final classification. So you have to be a little bit careful here. So yeah, SVM, SVM again. I mean, I think SVM, since I didn't cover, I won't know like what are the topics were covered, what was the flow, and the details I won't be able to cover. SVM will be covered by Maniul. If you have any more question on PCA, LDA, feature selection, or Bayesian network, elimination, just yeah, 1 second. Let me just open that slide. So one of the question is about this recursive feature elimination, where we basically um, okay. Let me just. Yeah, so one quick answer to that: would the most relevant features via PCA have the most relevant features via PCA? Yeah, large and yes, definitely most relevant features via PCA will have the large and I guess eigenvalues. I mean, you will have the eigenvalues and then you will sort it, and based on that, you will get the most important features. Uh, Filter and embedded methods of feature selection at top. So, what is this question? I didn't understand. Filter and elimination based features at selection at top level, that I couldn't understand. What comments can you made about the eigenvectors of the most? Yeah, the eigenvectors are basically let you get the directions where you want to project your data, basically, right? I mean, most largest eigenvalue you get, and then the corresponding eigenvector will basically give you the direction through to which you will be projecting your data, basically. Because eigenvalues won't let you project, right? It's just a value. It's a scalar, so it won't let you project. So eigenvectors will actually let you project the data to that relevant direction. Yeah, so recursive feature elimination. I think recursive feature elimination is basically the backward technique. So basically, you have I mean, you will have a bunch of features, and then you figure out which feature is the weakest at every point. For example, you figure out that so you could do it like this: recursive feature elimination. You have a bunch of features. You are training a classifier. Okay, you are training a classifier, and what you do is you remove. If you have n features, and every time you take one feature out, and with the remaining n minus 1 features, you build a classifier and see the accuracy. Okay, now out of all of these, you see for which of this feature the classification accuracy was the maximum. Okay, uh, uh, yeah, maximum. Okay, so that means by removing that feature, you didn't hamper the actual classification much, because if you had removed other features instead of this feature, your classification accuracy is being hampered much. So this is perhaps the weakest or the least useful feature. So you can just safely remove that feature. Okay, so your feature dimension reduces from n to n minus 1. Then you again do the same process again to remove the n minus the second feature, and so on. So the embedded methods are basically methods which are a part of your model. Like you have a machine learning model, and which are with like L1 regularization that will automatically let you select the features while you are modeling. Okay, so that doesn't need any. So in general, normal methods like wrapper or filter, you are perhaps doing it in 2 steps. Okay, like you have a feature selection, and then you have the build with the selected set of features, you are building the model. But while you are modeling itself, if your features are selected, that's what is basically embedded method. So you are applying some L1 regularization, which will let you select some of the subset of the features. Okay, so that's what is called embedded methods. And filter is basically you do not build the model at all. You just use some kind of correlation information, expect some correlation between the feature values and the final labels to determine what feature is useful. So for example, if you find a, so there are these these things, right, like correlation coefficient or mutual information, these you can capture. So whenever a label, whenever a feature is highly correlated, okay, or highly related to your final label, then that feature is useful. Okay, whenever they are not very correlated, that feature is not very useful. So these are called filter methods. Okay, you are computing some simple correlation, you are not bothered about the model at all, you don't even know what model will be built. You might build a deep neural net model, you might build an XGBoost model, you might build a logistic regression model, you don't know that. Okay, even before that, you just use some this correlation and see that what is your important feature and what is not. Okay, so that's the difference between filter and embedded method. Embedded method, you are building the model itself to figure out what is important. Filter, you don't build the model at all, you just use some sort of some what should I call it, some sort of related measures such as correlation or mutual information to determine these features are useful, and there is no relation between this and the modeling itself. The modeling algorithm could be different. Okay, and different modeling algorithms might have same set of features selected in filter method, whereas different modeling will let you select different features in embedded method. Okay, so that's sort of the difference. Is it possible to resolve the PCA components back into the original features? Yeah, it should be. That's a good question. It should be. So original features. So yeah. So the idea is in. Idea in. So yeah. I mean, it's a projection matrix. So so if you do the. So just a minute. So you see, you are doing a matrix multiplication. You are projecting it back to this space. So if you have the projection matrix, you should be able to move back to the original feature space with the inverse of this projection matrix. So that should not, I don't see that as a problem. Are you trying to ask something else? It's not very clear to me. Yeah, it should be. Yeah, I mean, or are you have come to the original feature space to this feature space, so you'll have exactly the data from the original feature space in any case. So why do you want to sort of move back? It's not very clear to me. Yeah, in Bayesian neural networks, yeah, you can use softmax or so softmax is not an activation function. Sigmoid or ReLU or 10H, these are activation functions. Softmax is a final layer function. When you are doing the classification, that's where you are trying to get probabilities of different classes at the final layer using softmax. So that's not an activation. Sigmoid is an activation function, and definitely sigmoid can be used in Bayesian neural networks also, as far as I'm concerned. No, so with that a possibility that you should be able to say the most important features. The most important features. Say it's hard to say. I mean, you have projected there is because each feature in the PCA space is a combination of the actual feature space. So the most important feature, obviously, in the through the projection matrix, you will know that this feature, my feature one in PCA is combination of my this much percentage of height, this much percentage of weight, this much percentage of width, and this much percentage of breadth. So you already know what are the importance to each what is the importance each you give to each of these original features to get arrive at this particular feature. So you already have that information. Yeah, encoder, autoencoders these days also people use. These are also these are also can be used instead of PCA LDA. The main difference between PCA LDA or autoencoder is in autoencoder, that's the idea. So you project your data to a lower dimensional space in a way so that when from this lower dimensional data you are able to reconstruct the original data as much as possible. Okay, so so yeah, so whereas in PCA, so these are the goals are different. Okay, in PCA you are trying to project your data along the maximum variance. Okay, in encoder you don't care about autoencoders, you don't care about projecting the data along the maximum variance. You are projecting in the data in some direction from which you will be able to recover your original data. Okay, so the loss function tries to capture that only. Okay, the original data, whenever whatever you are reconstructing the original data from the small projected data, that reconstructed data should be as similar to as possible to your original data. Uh, yeah, autoencoders are, yeah, it's reduce the loss. Yeah, autoencoders are tend to reduce the loss, and the loss is basically this is the difference between the reconstruction and the original variables basically. I mean, I mean, algos. Yeah, I mean, dimension. I mean, all of this can be sort of considered different ways to do dimensional reduction. No, no, orthonormal or orthogonal are not synonymous terms. Let me just tell you. So ortho, yeah. So orthonormal. There is so orthonormal is basically orthogonality plus you will have to normalize also. Matlab they are sort of unit vectors, whereas orthogonal is just each of them are perpendicular to each other. Okay. So two variables, I mean, yeah, two vectors when they are perpendicular to each other, they are orthogonal. But orthonormal is not only orthogonal, but they are also have to be normalized and be unit vectors. So they are different. If encoder decoder, if there is no activation function, if you have a complex system, then it differs PCA. The limitation of PCA originally differs to straight line. Yeah, so that's a valid point on encoder decoder. What you were saying that it's yeah, in PCA you are basically it's a linear projection. You know, encoder decoder you can have activation functions which can let you project the data in a non-linear manner. Yeah, but in PCA also there are kernel PCA and other PCA methods which let you sort of project your data in a non-linear space. So obviously you can do that in encoder, but that's I mean, in using PCA, some advanced version of PCA also you can do that using kernel PCA and other kinds of PCA. How can you visualize variance and correlation? What is the relation? Yeah. Relation. Yeah, correlation and variance. Yeah, it's sort of yeah. I mean, all of these are sort of different measures. There might be some visualization tools for covariance. I'm not completely aware of that visualization. Yeah, there might be some tools where you can sort of visualize covariance. But the diagonal elements in a covariance matrix are self variance basically the variance with itself. Encoder decoder technique being used in real life applications. Uh, See, encoder decoder techniques are they're quite trivial. So I mean, a lot of times people use those. I mean, so one example I know where people use encoder decoder kind of technique where they wanted to do this language translation. There they use these kinds of. It's a little bit more complex, but from one language to transferring to another language. or projected to a common space. Okay, so they what they do, you'll have language one, language two, they will project in a common space, and from that common space they will try to again project back to language one and language two. So those kinds of common projection techniques people have used. Even in my some of my earlier work I used that this projection kind of this autoencoder kind of architecture, multimodal autoencoders or something like that we have people have used. So yeah, but yeah, people a lot of times they will use this autoencoders as part of a larger network, may not be on its own. They often use this autoencoders, decoders as part of larger networks. But yeah, in general, encoder, decoder, if you talk about like a lot of times, I mean, even this encoder and decoder these days are referred to very generic kinds of things in complex neural network architecture. I mean, even if you think about this image to text conversion or on any of these, you are basically encode the text in some shorter format and then decode the text representation to get some other text language translation. All of these places encoder and decoders are used in some other way. Okay, may not be very simple encoder decoders, but maybe a little bit more complex. So I think we are sort of out of time here, and then there are obviously other topics to cover. So I'll sort of log out now, and I'll let Mainul and others to sort of take over and answer your other questions on SVM and other topics. Okay, thanks a lot for your time. It was very nice interacting with all of you guys.